טוב, איך הולך אז השיעורי בית, המטלות, החיים, כיף לכם?
משהו
כל מה?
כל תוצאות את צורת הבאות.
הוא תדע עברית, נכון? אנגלית?
לא.
English? עברית? Ni hao. Hello, you, yes. You speak only English, right?
Yeah.
Okay, so we're gonna have a tutorial in English today. So fun. So I hope you are having fun with the homework. You are enjoying every single part of it. Today we're gonna do infinite potential well. So this is actually the first true exercise we're gonna do. Up until now it was a lot of mathematical background, maybe a little bit of physics. Today it's gonna be more applied in a sense. We're actually gonna solve the Schrödinger equation from start to finish. It's gonna be like a summarize of everything we did so far in the course, and this is also gonna be like exam level questions in a sense. Exam level? Almost. Very close. Okay, the Schrödinger equation. So we have the time dependent and the time independent. We'll start with the time dependent, which is I h bar dot t. Let's write it with the wave function. Psi equals minus a plus square root over 2n psi plus v of x. So this is the one dimensional, and we actually, because it's some general differential equation which we know how to solve at that point, or almost know how to solve, depends on how far you learn the math degree. But we basically do it by separation of variables. We assume psi of x and t can be written as some function of x times some function of t. And usually, when does this work? Whenever we try, we don't have a lot of problems. What does it mean? We just plug in to the separation of variables inside, and we get I h bar phi of x t of t dot. Dot is derivative with respect to time. Equals minus h bar squared over 2m t of t. And let's call it, instead of phi, let's change it to phi to be consistent with the rest of the tutorial. T of t and phi of x double prime plus v of x times phi of x times t of t. So when we do separation of variables, we're just going to do it once. This during all the lectures, this course, during all the tutorials, we just assume there is some separation. Then we divide and try to see if we can separate an equation for time and an equation for x, or some general space coordination. And this is the way we separate. So the separation goes when we multiply by 1 over psi, or which equals to 1 over phi of x times t of t, and we get I h bar t dot over t, because we divide by t and phi, equals minus h bar squared over 2m phi double prime of x over phi of x plus v of x, the potential. We immediately see at this point we managed to have a separation of variables, because this is some constant, some function of t, and this some function of x. And when we have, let's call it f1 of x equals f2 of y, they can be equal for every x and y, just in a specific case where those two functions equal to some constant. And this is separation of variables, like the big idea. How will we call this constant? Any suggestions? You can say
Omega?
what?
Omega?
Omega is a good name, A is a good name, but the actual great name is going to be E. Because by coincidence, this is the energy.
Why?
Why? Why not? So let's say, so it's not why this is the energy, but when we build the Schrödinger equation, you can notice we can actually divide everything by IH bar, or multiply everything by 2. When we write the Schrödinger equation this way, we get exactly the energy, the separation of variables that gives us the energy. So why? Because this is how we define the Schrödinger equation. If we would divide everything by I, for example, so we will get here E over I. Okay. Those equations are very easy solvable. This equation in particular we solved like 4 times in the tutorials. When you have a first derivative of a function equals to some constant times this function, because what we have here is t dot of t equals E over IH bar t of t. We get that t of t, the temporal part, is equal to E to the minus, and I can just move the I upward, so instead of I here, I can write it I here and minus I E over H bar T. We're doing very basic stuff. This is stuff we should know out of in the middle of the night here. So we see here that in general, as long as we don't have some funny business, if this is equal to the energy, we will always have some oscillation for the temporal part. So we can almost always write T of t equals E to the minus I E over H bar T. Okay, this is fine. Okay, we're left with the other part of the special solution. The special solutions is also some equation we know how to solve, because we can write the special part as, we can write it as minus h bar squared over 2m phi double prime of x equals minus v of x plus, let's say, minus e times phi of x. So what I did, I just said, okay, this is all equals to e, and I multiplied by phi of x. Or another way to write it is phi double prime of x equals, so the minus is cancelled, so I can write phi of x plus e over h bar squared, and here we have 2m times phi of x. Or, in other words, a second order differential equation, which we also know how to solve. Okay? And when we have equation of the sort, let's do f double prime of x equals a f of x, the solution is a combination of sinus and cosinus, or two exponentials, which is equivalent. Okay. While this is the time-dependent Schrödinger equation, we usually denote h. Let's Okay, I'm getting a little bit messy. Let's clean a bit. We usually write, let's delete this line. We usually write H operator as the time independent. Shall I get the equation? So we write H operator is equals to minus H bar squared over 2m plus yan plus v of x. And when we apply it on some wave function, let's say phi of x, so if you apply H over phi of x, we get E times phi of x. We can see it also here that if we apply, I can rearrange this equation. Maybe here it's easier to see it. If we apply this operator of phi of x, so if we apply minus h bar squared over 2m phi double prime of x plus v of x times phi of x, we get exactly E times phi of x. And I'm not gonna solve for phi of x just now, but I'm gonna write it here in shading the equation. So h times phi of x equals E times phi of x. Usually, when we have boundary conditions, we get a quantization of the problem. And when we solve for a specific mode every time. So usually, we don't write just h phi equals E phi. We write h phi n, k, p, whatever the quantum number, equals En phi n. Now, when we want to combine where phi n of x is the spatial solution and t of t is the temporal solution. Now I want to combine it with psi of x of t. What we need to remember is here, this is a specific energy mode or a specific mode. So psi of x and t, we will write as a summation over all the modes from 0 to infinity, some weight, where Cn absolute value squared is the probability for the weight, times phi n of x times e to the minus I, e, and now I don't just write e, I write En over h bar t. Okay. I put it on the side, leave it for the whole tutorial. So this is very general. Here I didn't assume anything about the potential or about almost anything. You can still have the only thing I did assume about the potential is that we don't have any derivatives of it. So just assume something which is some very easy basic function of x. But usually that's all we are considering. Questions? Great. So everything is perfectly understood. Let's have a small example in any case. Small. Yeah. You can ask in Hebrew also. You can also ask in Hebrew. Okay, n equals, okay, I wrote n equals 0 to infinity, he told me, oh, but n equals 1. It depends on n of x and how you define n. So sometimes you define E1 as the ground state, sometimes you define E0 as the ground state. It doesn't matter as long as you're consistent. Good question. So let's assume n equals 1 is the ground state, because this is how they did it in this tutorial, but it really doesn't matter. You can define it however you want. And let's assume we have some solution for psi of x of t, which which looks like psi x of t equals 1 over square root of 3 phi 1 of x e to the minus I e 1 over h bar t plus, let's be consistent, let's write it minus I over square root of 2 phi 2 of x e to the minus I e 2 over h bar t minus 1 plus I over 2 square root of 3 of x e to the minus I e 3 over h bar t. So this is some example of a wave function which can exist. What we see here is we see that we have 3 different modes, n equals 1, 2, 3, where we can write C1. Let's write it in a column. We can identify this is C1, or 1 over square root of 3. This is C2 minus I over square root of 2, and this is C3. If you want to ask the question, what is the probability to be in the ground state energy? Or I can write it as probability to be in the ground state energy. Sounds very complicated question, and this is basically just C1 absolute value squared or a third. Similarly, if we want to ask what is the probability to be in the third energy band, which means be here, just C3 absolute value squared. Of course, if I did it correctly, and this is an actual physical wave function, I will get that a summation from n equals 1 to infinity of Cn absolute value squared would be equal to 1. If I would ask what is the probability to be in the 7th energy band, so probability of n equals 7, it would be equal to C7 absolute value squared, which is 0, because we don't have anything higher than 3. Good, great, very easy. I know it's easy. We'll do something a bit more complicated now. Questions? This is a very nice tutorial. It's well built. It's going to be one step at a time. And we're going to learn how to solve almost anything in this course today. Okay, so we have the Schrödinger equation. I didn't specify here almost anything. I just said we have some potential which doesn't have any derivatives, and operators which are not just multiplication by x. And in this case, this is the solution that I get, but it's not enough, because usually what we have is we measure the system. We are in the lab, we measure the system, we measure what is the probability to find the particle, and we get some. We don't get psi of x of t, we get some function which we can call it psi of x at t0. Usually we take t0 to be 0. So we made the measurement, maybe million measurements, to see what is where is the particle, and at what is this is where we're going to see it more or less. That is, we found the initial conditions of the wave function at some time, and our question is, what is going to be the wave function for some general time? Okay. The answer lays here, in this little magic. So first what we do is we develop the Schrödinger equation using the potential to get these relations. And now we can use the third equation to connect between psi x of t and psi x and t equals 0. So this is, in a sense, this is something which is similar to a propagator, because it propagates the wave function at time. Okay, we will hear more about propagators, but this is just the main idea. Okay, how do we do it? How do we solve this problem? So first I'm just going to write this equation, psi of x and t, but just for t equals 0, because I can do it. This is equal to sum over n equals 1 or 0, doesn't matter, Cn, phi n of x, and that's it. That's all. Okay. Now what we can do, we can integrate or make a projection, integrate both sides over all phi m star. So here we had phi n, here I'm gonna do phi m of x dx, and we're gonna get an integral over phi n of x sine of x, and this is conjugate 0 dx equals to a sum over n equals 1 to infinity Cn, and I'm just gonna make my life a little bit easier, phi m star of x, phi n of x dx. This is of course a delta function, which makes this is delta n m, of course from orthogonality, because I know phi m is the eigenfunction of the operator, so and the operator is Hermitian, so it must be orthogonal to each other and orthonormal even. And we get on the right hand side Cm, that's all, and on the left hand side phi m star of x psi of x 0 dx. Okay, I'd like to write it here. Cm equals an integral over phi m star of x psi of x 0 dx. And what I would expect from you to do in the homework is develop it every time, and what I would expect from you in the exam, to shoot it out, because it becomes obvious over time. So here I can also, because this is some arbitrarily integer, I can change it to n. And if you would ask me how to get psi of x and t using the initial conditions, I can say, okay, this is the, I can find Cn, the actual weights, insert it here, and all I'm left to is getting phi n of x. How do we get phi n of x? This is a function of the potential. Meaning we just need to solve, and I'm gonna write the function again here. I just need to solve the time independent Schrödinger equation, which is h, which is this equation. Usually h would be, not usually, always h will be minus h bar squared over 2m Laplacian plus v of x. We just operate it on phi of n, and we get the energies and the eigenfunction and the eigenvalues. Make sure it's clear what we did here. Questions, requests, comments? Nothing. You're all having fun? Is this make sense? Does it make you feel happy from the inside? You seem not enough. Okay. So up until now, what we did is we did something very general for the Schrödinger equation. Now we're going to solve the specific problem of the infinite well. So how does an infinite well looks like? Looks like this. We have here some function of x, and here we have some function of let's do it v of x, and somewhere between some 2 points we get infinite everywhere and 0 or some constant and some specific finite length. Very nice. How do we write it mathematically? V of x equals 2, and I can write it as 0 between where x is between 2 points. Usually we will denote those points as 0 and L, because if it's between A and B, I can always move the problem, change coordinates, and solve it for these new coordinates, and infinite otherwise. Make sense? Okay, so this makes some constraints, some physical constraints on our wave function. It makes our wave function psi of x and t. It makes it be something between the boundaries and 0 everywhere else. So when the potential is infinitely large, the probability for a particle to be found in this region is 0. It's absolutely 0. There's no way to find a particle and where the potential is infinitely large. Makes sense, right? So when we will get into what is tunneling and how we tunnel, it's not like a ball that we kick at some wall and it bounces back, because in this case the ball thinks there's an infinitely large potential wall. It's going to be something more finite, and then the particle, which is a lot smaller than a regular ball, can actually tunnel through. But here, because it's infinitely large potential, there is absolutely no way to get inside the wall. Okay, let's actually solve the time-independent Schrödinger equation. It's actually very easy. We do minus h bar squared over 2m dou x squared, because this is just one dimension, plus v of x, psi of x equals, and let's write it psi n, en times psi n of x. And because this is actually only the spatial part, we can write it as phi, not as psi, to make it less confusing. So what is v of x? When we are in the walls, it's absolutely infinity. And we know the solution. We can write it, also here we can write phi n of x. The solution is 0. So we care only when there is no wall at all. So we can minus h bar squared over 2m dou squared of x, phi n of x equals e n phi n of x. Or dou squared of x, phi n of x equals minus 2m e n over h bar squared phi n of x, meaning phi n of x is a sine of kx plus the cosine of kx, where k is what? Square root, right? And actually it's not just k, it's yeah, you can write it as k. Right over that. Okay. I don't want to fully solve it because we solved it a lot of times. What I want to emphasize is that the cosine part vanish due to the boundary conditions, because we have both conditions, both sides at x equals 0 and L. We must get phi n of x equals 0, and the only way to satisfy this condition is using a sign. Then we get a quantization over k. We get that k is n pi over L. So k actually is n pi over L. And we get phi n of x equals a times sine n pi over L over L times x, of course, kx, where a can be found for normalization, because we know this is an eigenfunction. Okay. Let's just write here the summarization. So for the infinite potential well, infinite potential well, we get that phi n of x is square root of 2 over L sine of n pi over Lx. And because we know that what we have in this side is the square root of this function, of this coefficient, we get also the energies, the eigenvalues, or the eigenenergies. En is h1 squared over 2n n pi over L squared. So we started from a very, very big general problem, and we narrowed our view to specifically infinite potential wells of size n. How we did it? We just solved the time-independent Schrödinger equation using boundary conditions. One thing to note is that because we have a sign, only solutions of the sign, so we have a sum of infinitely different numbers of sinus functions, we know it makes us have only some specific parity for the problems. Okay, we don't have any cosine, so the boundary conditions affect the parity of the problem. Makes sense?
What do you mean by parity of the problem?
Even odd, so we don't have any like cosine function. So it will start from 0, finish at 0. It just, I don't want to get too much into it at this point. Just saying, we don't have a cosine, we have only sine of x. So we have only specific parity, specific symmetries that are allowed in this problem. Okay. Wait, we are almost done. No, we have a lot more. But we're almost done for the important stuff. Because if you know how to handle the basic ideas very good, it's going to be very easy to implement it for harder things. I know it's fun, because it's not. It's actually very hard to do at the beginning. In any case, we solved for generally the potential well problem. But you can say, Omer, but we have here phi n of x for a specific mode. We don't have psi of x and t. We don't know actually what is the wave function in general. And the answer is correct, but the reason is we don't have enough information yet. What we are missing to actually have psi of x and t, the wave function for everywhere, for all the time, is some initial conditions. If we get the initial conditions, and we already know what are the eigenfunctions, we can get the weights, and then we have psi of x and t. In a sense, phi n of x was found using the boundary conditions of the problem. So it's infinite here, it's 0 here, or in other words, the potential deduced as phi n of x. And C of n, the probability to build every specific mode, is deduced by the initial conditions, or the boundary conditions at time. So I love to say that there are boundary conditions in space, but there are also boundary conditions at time. Let's say we have the setup of this infinitely large well. Can we have psi of x and t, which looks like this? Does it make sense?
Yes.
Yes. Why? Because it doesn't matter how ugly it looks. We can still, if it is 0 and the boundary condition, if it fulfills the constraints, we can explain it, we can demonstrate it by this infinite series, because this is spans the whole space. So it spans all the full possibilities. We can have anything in the middle. Can we have something like this? No, because it has to be 0 in there. Okay. Some general intuition. Usually it will be more something like this. With some negative signs. Okay. Great. We have a lot of fun. Okay. Let's do a the simplest example to warm up. Let's say I have this infinite potential well of length L, and I have the specific initial conditions of psi of x at times 0 equals to minus square root of 2 over L sine of 7 pi over n over L over Lx. Okay, this is actually very easy. So we can solve for Cm and find all the coefficients, but we actually can also write psi of x and t. We can actually cheat here a little bit, because this problem is so easy, and write it as C1 phi1 of x, and let's write psi of x and t equals 0, plus C2 phi2 of x, plus C3 phi3 of x, plus that, and write here all the infinite amount of terms, and do mix and match. If our eyes are very sharp, because here we have 7, we can write that it equals actually just to minus square root of 2, and let's write it as, to be more precise, it should be minus 1 times phi 7 of x. Because what is phi 7 of x? It's square root of 2 over L times sinus 7 pi over Lx. Hence, I can want Cm in general to be minus 1 if n equals 7 and 0 otherwise. And I actually solved the whole problem, because I can write psi of x equals t. So it's the full series, but only n equals 7 survives. So it equals to minus 1 phi 7 of x e to the minus I e7 over h bar t.
What? How do you do it?
The Chazal?
How did you
So here it's a minus. Why did I add a minus 1?
Yeah.
Because this is the initial conditions. I can write it as an infinite series. This is what I did it over here or here.
Yeah.
But I noticed that the only mode that I have here, the only sign I actually have is of phi 7. Sinus when n equals 7.
Yes.
What is phi? So I can write it again. So this is minus 1 times. What is phi 7 of x? It's square root of 2 over L times sine of 7 pi over lx, correct?
Okay.
So this is just a -1 that comes from here,
Oh.
and it just stays.
Okay.
Realistically, we'll never get psi of x and 0. We'll get the square of, right?
Again,
Realistically, in the lab, we'll never get psi of x and 0. We'll get
a specific sign. You mean like this is not realistic in your opinion?
no, the bottom one. Like, what? No, not the bottom side. The second from the top. Yes, we'll never get.
Why we always get it? This is what we always get. But I don't know what I didn't specify C1, C2. They can all be 0. They can be whatever.
Yes, but in the lab you'll never get that. You'll get that squared, right?
Of course, yes, of course. Because when I measure a specific thing, I measure a probability. So what I actually get is I try to measure if an electron has a specific energy. Let's leave out the side. And if it has a specific energy, I know, oh, it has its specific energy. I don't know anything about the probabilities. But if I check it 1 million times, I get the probabilities. From the probabilities, I can take the square root and get the C's. Correct. Up to some global phase.
The sign, like the -1, you'll never know if it's a -1 because you'll have it squared in the data.
Yes, but what I can know is if I have a superposition, let's say, this is a great question, let's move to the next example. Let's say I have, not minus square root of 2 over L, let's say I have square root of 1 over L times sine of 5 pi over Lx minus 1 over L square root sine of 7 pi over Lx. So in the previous example, I wouldn't know if there's a minus or not when I measure it. Here I would know because this state will oscillate with some phase with respect to this state. I can also write here as a plus and multiply it by e to the I pi, where the phase is pi, because e to the I pi is equals -1. Of course, when I measure it individually, I wouldn't know. But when I measure it with respect to each other, I would know there is a minus. Maybe what I wouldn't know is maybe I say here it's a minus, okay? But what I actually measure is this times -1. So I can multiply everything by -1 if I want, or add some global phase, e to the I pi in general. For the second example, let's say we have a sum of 2 modes for initial conditions. What we get is, and let's put this to the bottom and talk about it in base. What we get is, and we can still use the little kid's trick, and we get, okay, what we have here is 1 over L square root, and here we have square root of 2 over L, which is actually 1 over square root of 2 phi 5 over x minus 1 over square root of 2 phi 7 over x. Does it make absolutely sense how I came from here to here? If it doesn't make sense to you, let me know right now. If you're not absolutely sure why. It's okay to ask questions. We're here to ask questions. Okay. So basically, if I take phi 5 of x and just insert this, we're going to get square root of 2 over L, and the square root of 2 will cancel each other out. The same for phi 7. And also, we see what is the probability to be at mode 5. It's going to be, so the probability to be at energy, let's say at n equals 5, it's going to be 1 over 2. The probability to be at n equals 7 will also be 1 over 2, which is just the coefficient absolute value squared. Overall, the probability to be in sum mode is 1, because we're always sum. And we can write, okay, now it's a bit more complicated to. Okay, so we know psi of x and t, which is equal to just 1 over square root of 2 phi 5 of x e to the minus I e 5 over h bar t minus phi 7 of x e to the minus I e 7 over h bar t. But the question can be, what is the probability p of x and t? So it's very easy to just say, okay, just take absolute value of this plus absolute value of this, but it's not the same. It's like an absolute value of everything, which is what we should. Let's do it slower. So up until here, we know. So here, p of x and t, it will be 1 over 2, and when we take the absolute value square, because phi of x is real, I'm not gonna indicate the conjugate, but we should do it. What I'm gonna just write, I'm gonna write phi 5 e to the minus. Let's take first the conjugate. So e to the plus I e 5 over h by t minus phi 7 e to the I e 7 over h by t times phi 5 e to the minus I e 5 over h by t minus phi 7 e to the minus I e 7 over h bar t is equal to 1/2. So the first multiplication will give us phi 5 absolute value squared. The last one will give us plus phi 7 absolute value squared. But if we consider the intermediate terms, we get plus phi 5 phi 7 e to the I e5 minus e7 over h bar t plus phi 7, and here we actually have minus, and also here we have minus phi 7 e to the I e7 minus e5 over h bar t. Okay. Interesting. So this is what we would expect in general without the discount, but we actually get another term. And here it's not just phi 7, it's phi 5 times phi 7. Or phi 7 times phi 5. Yeah, it's the same. Okay. This is, let's write the first part again. So phi 5 absolute value squared plus phi 7 absolute value squared. And then we can write it as minus 2 phi 5 phi 7. And what we have is e to the I x and e to the minus I x, which is basically a cosine because we add them together. And so we get the cosine of e5 minus e7 over h bar t. Okay. This is very, very interesting because it has some physical meaning. So if we would go to the simple problem here and we try to get what is p of x and t here, this is very easy. We'll just get phi 7 of x absolute value squared, because this is gonna kill itself. Here we got something, a whole different solution. We got this. This is p of x and t. You get a whole different solution. So although we started from some combination of psi 5 and psi 7, which were very distinct, here we have some not so distinct combination. We get some probability to be psi 5, psi 7, and here it's something in between. what does it mean in between? So we could be, what we have here is we can be somewhere at psi 5. Here we could be somewhere at psi 7. Here we could be maybe here, maybe there. And we get something which depends on time. To put it in a figure, let's say we have here E5, and here we have E7, the energy bands. When we start in a superposition of the two, we can move between the two. If we start just with E5, we are stuck there. So here some of the times will be more at E5, some of the times will be more at E7. And it's going to oscillate over time. With and the oscillation frequency will depend on the energy gap between the two. Yes?
Is it normalized?
Sorry, XT, of course.
So it's half times.
Yeah, I mean also P of XT, because say half of the time here, half of the time here, right? Here on average it will be on 0, because sometimes it will be more on psi 5 and less on psi 7, and sometimes it will be more on psi 7 and less on psi 5. It's like something that takes some of the probability to be here over here, and sometimes it takes part of the probability of being here to be here.
Yeah, but it's half times if what's inside the brackets is basically 1 plus 1 minus the whole cosine term, right? Or is it not 1? The phi 5 squared.
Okay. When you have so here say you have 1, and here we have something which is not 1. Alright? And it's problematic because we can have probability of 1.5. And we also can have probability of half. But what we have here is something which oscillates between one and another. So on average, you will get a probability of 1, of being somewhere. So if we integrate over all time, what we're going to get in this term?
0.
Exactly. But at a specific time, this might change the probabilities of being more at some specific energy level or another one. This means if we have initial conditions which involve some different modes, it means we can move between those modes over time. And if we have only a specific mode, we stay at this specific mode forever. So much fun. Such great ideas. Okay. So in general, in quantum mechanics, when we have a system in some superposition and we evolve it over time, the superposition will get mixed up over time. It makes sense because if we have a specific energy, E7, and that's it, and that's all what we have, there is no reason for us to get more energy. There's no reason for us to lose energy. We're just going to stay there. But if you have two possibilities to be sometimes here, sometimes there, it can mix up over time in some predictable way. Great. Okay, so when taking absolute value, make sure you don't just take the absolute value of this and then plus the absolute value of this. You do the full math because it's going to get different results, obviously. Let's move on. Now we talked a lot about position space, or the spatial space. Let's talk about momentum space. Ooh, momentum! We love momentum. I need a t-shirt saying I love momentum. let's assume we have a particle in the ground state. So let's give a few words to get more familiar with words and not only mathematical tricks. Let's say we have some particle in the ground state. Ground state of a potential of an infinite potential. Well, so all of these words we heard today already. So we have a particle in an infinitely large potential well, and it is specifically at the ground state. In other words, psi over x at 0 is equals to square root of 2 over L sine of pi over L x. Okay. We now want to find the probability distribution of the momentum. Okay, probability distribution of the momentum. So if psi of x is the probability distribution of space, or let's leave time out of this question and just the probability distribution of space, we want to find the probability distribution. So this is the probability wave function in space. The probability distribution at space will be p of x equals psi of x square root squared. This is the density. So sometimes we call it rho, and sometimes p or rho of x will just be psi of x absolute value squared dx. A lot of people are confusing this because also the hormones can be confusing sometimes. But this is the density and this is the actual probability because of the dx. We want to find this one of psi tilde of k, or to be more precise, to find the probability distribution of k. Let's have it tilde because it's k in k space. Okay. So we can write p of k. Tilde is absolute value of psi of p or rho, it doesn't matter. What we care is the psi absolute value square root of k. So first we need to take the Fourier transform of psi of x. And then we need to take the absolute value and square it. למה לא עושים ככה? פרוב אוקיי? פה פשוט ההבדל בין פרוב לרוב זה שרוב זה ב-dx ופרוב זה עם dx.
עם dx זה אומר עם האינטגרל.
כי עם dx זה ממש כי מה ההסתברות ליצור חלקיק במקום מסוים? אז פסאי של x בריבוע dx. פסאי של x בריבוע זה תמיד יהיה 0. בכל נקודה ספציפית, כדי לעשות dx. אם אתה רוצה הסתברות ולא צפיפות הסתברות. וזה ניואנסים יחסית קטנים. לא אנחנו פשוט, P זה יכול להיות צפיפות הסתברות, זה יכול להיות הסתברות, זה לא כזה משנה, כי אנחנו לא כאלה מעניין אותנו. בסופו של דבר, כשאלתי מה ההסתברות בין נקודה א' לב', נעשה אינטגרל P של x dx. או רו של x. בכל מקרה, anyway, when we need to find P tilde of k, we can take psi tilde of k absolute value squared. So we first need to Fourier transform. So psi tilde of k is equal to integral minus I kx over square root of 2 pi psi of x dx. Whew. Which can be equal to psi tilde of k is equal to integral minus I kx over square root of 2 pi square root of 2 over L sine of pi over L x dx, which is exactly 1 over square root of pi over L divided by pi over L squared minus k squared e to the minus I k L plus 1. So this is psi tilde of k. Of course, I don't solve integrals, although if you would ask me how to solve this integral, I would say sine of kx, I can write it as an exponential, as a sum of two exponential, and then solve it. Or equivalently, I can write the exponential as a sum of sine and cosine and solve it. Of course, it's the boundaries. If you ask me about the boundary, it's gonna be between 0 and L. This is why we don't get essentially some crazy stuff. It's the definite boundaries. Solvable. I don't care how you solve it. Just solve it. Okay. We are not done yet. We need to find p tilde of k. Meaning we need to take the absolute value of this squared. And again, I'm not gonna do it. Okay, let's do it partially. Let's write it as. Let's do part of it, just for the fun. So the first part is very obvious. We just take the square of it. So we can write 1 over pi L times pi over L divided by pi over L squared minus k squared. And then we have absolute value of e to the minus ikl plus 1. And now absolute value squared. And now we need to take the absolute value square of this, which all I want to do is write it as e to the ikl plus 1 multiplied by e to the minus ikl plus 1. I do make an emphasis here because it's very easy at the start to say, absolute value. It's very easy, we just don't do it properly. Do it in a lot of different ways, which is not the proper way. So make sure when you have something which is complex, you do it very carefully and properly. Because usually, one way to figure out we didn't do stuff properly is when we operate an absolute value and then we get something which is complex. And we are like, oh, sorry, so the probability is not minus 5i. No, it's not. In any case, I just want to write, so here is the tilde, p tilde of k is equal to 4 over pi L, pi over L divided by pi over L squared minus k squared, cosine of k L over 2. Why did I went through all of this? Because you're going to do it a lot of times. And I want to do it at least once. So let's have another overview of what we did. We did something which, when we do it in the homework or the exam, it's going to be a bit harder, a bit more rigorous. But it's very simple. I had psi of x, and I want to see, okay, what is the probability to be at some k at momentum space? So we don't. So what we do is we basically just transform from psi of x to psi of k, take the absolute value, take it to the square. What we did find out here is while in x it's very definite where it is. It has some specific sign. So if we plot it just like a specific sign in space, it's very easy to look at it. Here it's not very easy at all, p of tilde of k. It's not very obvious what we see here. We do see cosine of kl over 2, which is a bit weird from parity-wise, but here we have some offset with the k, so it's a bit confusing. Because this is, in a sense, this is the probability of the momentum. What we can, let's see if we talk about it a little bit. We can say p of k is symmetric in k, so p of k equals to p of minus k, which makes sense because if we have some symmetric boundary conditions, you would expect the momentum to be okay, have the same probability to go to the right as going to the left in general. So we can go to the right and left at the same probability, and the same probability for specific momentum. So this is one thing. We see it has some oscillation, which depends on the value of k and the length L, so it oscillates from one momentum to another. Also makes some sense because of the priority, we had to have some solution. The thing is, the question is, wait, what happened when k equals pi over L? So it looks like we have some critical value here, right? Because when k equals pi over L, here we have 0. And we divide by 0, so we have infinity. No, wrong. If we have k equals pi over L, cosine is equals 0. So it's fine. But you always need to check those stuff. I want you to have a solution. I want you to check if we have criticalities, if it makes sense, symmetry makes sense. Because it's very hard to get lost in the math and in the equations. But if you try to think a bit, or does it make sense physically or not, it's very good. Both in homework and the exam, if you got something that is very weird, you can just write down. I got this solution, I think it's correct, because that's and that. Or it doesn't make a lot of sense because of the symmetry and the anti-symmetry of the problem. Okay? And that's it. Really, really good. It's really, overall it's very easy subject. Kind of. It's very easy when you understand it. And when you get used to having the Schrödinger equation, solving the time-dependent Schrödinger equation, and just get the eigenfunctions, eigenenergies, and then just play with it. I want you to ask questions, like bigger questions, about the ideas, about why do we do this, why do we do that, what does it make sense. So think if you have something like you're not clear why we are doing what we are doing.
Is the probability on the momentum space is the same as the probability in the כאילו, האם זה אותו לקבל את אותה הסתברות? אם זה יהיה במרחב של התנא ובמרחב של ה-X?
פה אנחנו רואים שלא, פה אנחנו רואים שההסתברות פה היא פשוט
ופה
שונה.
זה לא אותו דבר.
זה לא אותו דבר.
אוקיי. אז היה איזה תרגיל בבית הראשון שהיה כזה, הייתה הוכחה כזאת שזה שווה.
שיש קשר. Okay, בהחלט יש קשר. So the question is that, do we have any relation between the probability in caseless and X-best? So yes, definitely yes, big yes, huge yes. We have something called N-fest, which we'll get to in a bit. But more than it, we see this is a Fourier transform. It's a Fourier conjugate, and also last tutorial we talked about the uncertainty principle. I mean, if we know a lot in X space, we don't know anything in K space. And this is where we're going to see it in the probability functions. If you don't know anything in X space, we're going to know a lot in K space. So yes, it has a lot of relation. Okay, I want to do some more complicated example now. Now we want to do something which is really complicated, so if you're not sure what you're doing here, now we're going to have a fresh start and try to be focused. We're still in the infinite potential well. We're still infinitely beginners. But sometimes you're going to get finite. Not today. Let's say you have some interesting initial positions, psi 0 of x, which can be written as psi x and 0, so that's just notations, equals ax times l minus x. Oh no, I cannot find the coefficients as easily as before. Okay, first thing we do is we plot it using the decimals, your mind, or anything else you want. Okay, so between 0 and outside the well, we know the probability is 0. We also can observe that when x equals 0, we get 0, and when x equals l, we also get 0. And what we get is some formula
more.
In the middle. Somehow what shape? Okay. First thing we always do is we find A. How do we find A?
The space.
What we do?
Integration.
Normalization, great, normalization, integration. Exactly. As let's write here square root of 30 over L to the 5th. But I'm actually, most of the time, just gonna call it A. Because I don't want to write too much. But if I'm gonna do an integration of psi absolute value squared dx from x infinity to infinity, which is gonna be immediately reduced to an integral from 0 to L, because everywhere else it's 0. I'm gonna constrain it to be equal to 1 and get the normalization A. Now, our question is, what is psi of x and t? Okay, this is the question. This is the big question. How we do it? So, we first, so Vn of x, we know those are the modes because we have an infinite potential well. Doesn't matter what are the initial conditions, those are our wave functions because we solved it specifically for the potential. All we are left with is finding the CNs, the coefficients or the weights, and that's it. And then we won, and then we can just insert it here to the infinite sum, the infinite series, we won. So Cn is equal to an integral. And instead from here, let's say it's from minus infinity to infinity over all omega, all the space, it's only going to be from 0 to L, because this is everything else, it's absolutely 0. And we're going to have square root of 2 over L sine of n pi over L x. This is phi n of x. And now we're going to write psi naught of x. So we have square root of 30 over L to the 5th times x times L minus x dx. And now we're going to solve it. Sin of x times x or times x squared we can solve by integration by parts. All the trick I taught you last time. You can take a derivative with respect to n even. So homework, you will do a lot of stuff like this, but it's essentially solving an integral, which if you have trouble, feel free to come to me. But I don't want to lose your attention and I want to emphasize on other stuff. And if we solve this integral, which you will do in your homework, stuff like this, you will get Cn equals to 0 for even values of n, and a times square root of 15 over n pi to the cube for odd values of n. Okay. Another overview. I'm going to repeat myself a lot. What we did here. We had the problem of infinite potential world. We have from here, from 0 to L, the potential itself, V of x. We took V of x to the Schrödinger equations and we found the wave functions, or the eigenfunctions, and the energy levels, or the eigenvalues. So we basically solved the eigenfunction, eigenvalue equation to get those specifics. Then we use the projections to say, okay, if we want to find psi of x of t, we can find what it is at t equals 0, which is usually the initial conditions. Then find c of n, and that's it. I just solve for c of n. So here, I'm done. I'm happy. I don't need to do anything else in my life. What we usually do after this step is we try to start and analyze other stuff. For example, let's say I'm interested at, okay, first of all, I think psi of x and t is just like in Cn. put it in here inside here. But let's say I want to know what is the probability to be in a specific energy state. Okay, so what is the probability to be at energy n? What will it be equal to? Cn squared. Exactly. Cn absolute value squared. Perfect. Now another question. מה השאלה? מה הסיכוי להיות ברמת אנרגיה? What is the probability to be in a specific energy level? Just the coefficient squared, just the weight. I asked it in a little bit of different question. Like before I said what is the probability to be at n, and then I said Cn squared, right? But now I said energy. What's the difference? No difference. It's the same, but it's good because now we learn new words. We're not going to get stumbled by the notation. Okay. Now, so now I want to ask something which is a bit more, maybe complicated, but just maybe. What is the average energy? That's average energy in a specific time t. What is it equal to? Okay, now we get to observables. You need to shout at me if you want me to hear. or shut up. but you can shout.
אני לא בטוחה.
לא, זה בסדר אם את לא בטוחה. את יכולה לנחש. זה לא שזה מוקלט, כולם יראו. סתם, אף אחד לא יראה את הלחש.
כאילו C1, כאילו probability כפול כאילו E1 ועוד 2.
So the suggestion here was let's sum from n equals 1 to infinity Cn absolute value squared En. This is absolutely correct, but why? So it makes sense, right? It makes sense. It's a good reason, especially when you don't know what to do. It's really good reason to say it just makes sense. It's true. This is how to calculate the energy, but we can do it more rigorously. We can write it as psi E psi, right? This is my definition. I'm gonna just for now delete it, but this is absolutely correct. Psi E psi. I can write it like this. I can then open the integral and write. Let's write it psi, and actually the operator is H operator. So let's write dx psi of x and t conjugate H operator psi of x and t. Let's write it using the full definition of psi of x and t. Let's write it as dx sum of n equals 1 to infinity Cn phi n of x, and we can have it actually conjugate because why not? E to the I E n over h bar t, and H operator sum over m equals 1 to infinity Cm phi m of x e to the minus I E m over h bar t. Okay, and notice we can use actually the term, because this is H operator, we can use it this definition H over phi. We can do it, we can apply it, or in other words we can take almost everything outside, so we can have sum over n equals 1 to infinity, sum over n equals 1 to infinity Cn star Cm. We can also take e to the I E n over h bar t, e to the minus I E m over h bar t, and then integrate the x. And this is the only things we can take out. Phi m conjugate of x, phi n, sorry, and phi m, and here h operator over phi m of x. Okay, does it make sense what I'm doing this far? And when I apply h over psi, I get em of x. Overall, from this integral, I get em, because em doesn't depend on x, times delta m n. So I can cancel one of the two summation and get a sum from n equals 1 to infinity. Cn absolute value squared. This and this, they just kill each other. So this is En, this is minus Cn, and we get En. What we did, we had some intuition and it was correct, but we didn't know exactly why, where it came from. We actually could prove it. This is what we did. We proved this equation that the average energy is just the summation of all energy levels, where for each energy level you take the energy times the probability to be in this energy. It's like Bayesian theory, very, very obvious, but why it works. But we need to make sure it is consistent with quantum mechanics, as we learned. Okay. Questions so far?
I think the result this result is the original definition, and that representation phi is just it should just be a result. So I think this is.
Because we said this is a definition,
yeah,
and what we have is just a result.
Yeah.
Yeah, a lot of the times what we do is we have some definitions or some stuff we know we are correct, and we need to make sure they are consistent with quantum mechanics, because in quantum mechanics it is not just regular statistical physics or statistics. It is statistical physics or statistics with some additional postulates. So how do we know the Schrödinger equation is actually works? How do we know it's a true description of the physical world we live in? How do we know Schrödinger equation is not just some rubbish? So we need to check it in any way possible, make sure it is always consistent, always gives us what we think. Does it answer your question? We need to check. It is true that here this is obvious because this is a definition in a sense. Because what is the average energy? It's the energy times the probability to be in the specific energy. But what is average energy in quantum mechanics? I'm not sure because it's some new world we created. Of course, it's the same. It's consistent. And if it wasn't consistent, we were in a big trouble. Okay. Airfast. Let's give a few words about Airfast. Airfast is one of the things which are very, very cool and which you will learn mostly in the lectures. It is very basic in a sense when you just look at the equations, but you can actually derive those relations which I would want to do. And one of its theorems says that the average momentum can be written as the mass times the derivative of the average x over t. So in classical mechanics we know this as P equals mv, right? So haha, big surprise. But in quantum mechanics the fact is that it is not right. P doesn't equal to m times the x to the t in quantum mechanics. It's not the same. Because when you have a specific operator, it's an operator. It's not an. It's not. It can be. You can apply the operator to observe something and get an observable, but observables are not some operators by themselves. Meaning H is an operator, but E, the energy, which equals to H, like the observable of the operator, this is something you see. This is not something like H operator is not something you can measure exactly. It's some operator. This is a measurable object. Similarly here, P is not an observable, but the average value of P is an observable. So the average momentum can be observed, but the momentum it's not something. And why it is not an observable? You can say, oh my, I can just see what is the momentum. But when we talk in quantum mechanics, the momentum of a specific electron is not defined solely by a specific value usually. It is usually some variation or some function, some wave function of momentum. Some function of the momentum or some wave function of the space. However, because we have to see consistency in quantum mechanics, if we take the average value of P, we get exactly m times the derivative with respect to time of the average value of x. So observable wise, it's gonna satisfy classical mechanics. Here, for this specific one. Not necessarily for everything. Questions?
תנסה להוכיח את זה עם פשוט...
אפשר להוכיח את זה, אני לא מתכוון להוכיח את זה. אין לנו זמן לזה. כן, לפעמים יבקשו בכלל להוכיח את זה. תגנים. איך להוכיח את זה פשוט? תחשב את המומנט הממוצע ואז את ה-X הממוצע ולא חושב שתגזים את זה לפני זמן. questions, שאלות. טוב, זהו. כן.
שאלה.
וואלה זה מביך. יש לך קישורי מסך את המפה של הקמפוס? זה ממש מביך. אני גזמת. זה כאילו מעל המקום. הכל רע, הכל רע.